Chapter 20, Lesson 1. In this chapter, we will be speaking about a section of chemistry called electrochemistry. And this essentially will involve the connection between chemicals and electricity. And the way this is done, practically, is through a battery. A battery uses chemicals, essentially, to produce electricity. And we'll take a look at some of the concepts, some of the background to how this works. We're going to introduce a reaction as an electrochemical reaction if there is electrons, there are electrons being transferred from one substance to the other. Very often these are called oxidation and reduction reactions, redox for short, because in one of these reactions you have both oxidation and reduction happening. So a famous example of this is what you see on the right here. This is just a ribbon of magnesium immersed into an acid, most likely hydrochloric acid, and these bubbles that you see being formed are actually hydrogen gas. There is an electron that, two electrons actually, that go from the magnesium to the hydrogen in hydrochloric acid, and as those electrons are transferred, hydrogen is liberated. And we can take a look here. Here's an example of an actual equation where this happens. Instead, here we have zinc instead of magnesium. But if we take a look at the oxidation numbers, these are kind of like the charges of the different species. Anything in its elemental state, like zinc, has an oxidation number of 0. And then on the right side, zinc has oxidized to a +2 charge. And in so doing, it actually lost 2 electrons. Where did those electrons go? They went to hydrogen, which began with a +1 charge and ended with a 0 charge. Hydrogen accepted those electrons and became neutral. So in order to work with these redox equations, reactions, we'll have to keep track of electrons that are being lost and gained. And we'll do so by first assigning these oxidation numbers. So let's kind of review or show you how these are actually determined, these oxidation numbers. So anytime a species is oxidized, oxidation is by definition the losing of electrons. Now, the reason we call it oxidation is historically it was connected to oxygen. So any substance that bonded to oxygen itself actually lost electrons, and those electrons actually went to the oxygen. That's why it's called oxidized. But oxidized means we're losing electrons. And if you take a look at zinc again, zinc begins with a 0 charge and then ends up with a +2 charge. Zinc has been oxidized. It has lost electrons. And then hydrogen began with a +1 charge, ended up with a 0 charge. Hydrogen actually gained electrons, and so it got reduced. So if you recall, there was an acronym we can use for this, oil rig. Oxidation is losing electrons, and reduction is gaining electrons. So this may help you remember it. And remember, what you're doing is it's always in terms of electrons. So you're losing electrons or you're gaining electrons. Another way of looking at it is reduced means literally what it sounds like. The charge gets reduced or goes down. So the species that gets reduced, in this case hydrogen, goes from a +1 down to a 0. And then the other guy gets oxidized. So there's another term here, another piece of vocabulary that we will be using. The substance that gets reduced is called the oxidizing agent. So in this case, hydrogen gets reduced because it goes from a +1 to a 0, and hydrogen is called the oxidizing agent because hydrogen oxidizes the other species, and it does so by taking his electrons from him. So that's why hydrogen is called the oxidizing agent. Hydrogen helps zinc get oxidized. And then by contrast, zinc actually, while it's oxidized, is called the reducing agent. So zinc here, you can say, gives electrons up to hydrogen, therefore reducing hydrogen, so it's called the reducing agent. So these are also involved in oxidation reduction reactions. In this first lesson, we're going to take a look at these oxidation numbers, how to assign them, and how to determine what gets oxidized and what gets reduced. So we'll go through some of these rules, oxidation number rules. Think of oxidation numbers as kind of a charge, but not every one of these is going to be a real charge. Some of these, as you'll see, will be charges that are hidden inside of the compound, but they're never really you can never see them in solution, for example. There's a difference between charge and oxidation number. These actually are not synonymous. These don't mean the same, even though both will involve assigning some sort of number with a charge. So firstly, elements in their elemental form have an oxidation number of 0, zinc or magnesium or oxygen, if they're not bonded. So elemental form means they are not bonded with any other element. The oxidation number of a monatomic ion is the same as its charge. So for example, chloride, the oxidation number there is -1. This is a true charge of chlorine, -1, and it's also its oxidation number. Nonmetals, in general, tend to have negative oxidation numbers. This is because nonmetals are closer to the noble gases on the right side of the periodic table, and they must gain electrons to become stable. So they're usually negative. And oxygen is right there, so oxygen almost always has a oxidation number of -2. The exception is when it's in a peroxide form. And peroxide looks like this. Essentially, you'll see, for example, H2O2 is hydrogen peroxide, K2O2 is potassium peroxide, and in this case, oxygen has a -1 charge. And there are, the way you can see this is because there are two hydrogens balancing two oxygens. Each hydrogen is +1. Hydrogen cannot be any other charge since it only has one electron to lose. So oxygens must also be -1 to balance them out here. But this is kind of rare, and really in just one or two cases you'll see this. Usually oxygen is a -2. And hydrogen then is usually +1. It could be -1, and it'll be -1 only in the case when it's bonded with a metal. Hydrogen is usually bonded with nonmetals, as famously in water, so it assumes a +1 charge. When hydrogen is bonded to a metal, like in what we call metal hydrides, then oxygen becomes negative, but it'll always be 1. Hydrogen cannot be 2 or 3 or anything beyond just 1. So oxygen is -2, hydrogen is +1. These two elements will help us determine the oxidation numbers of most other elements in compounds. So here is a little more about nonmetals. Fluorine will always be -1. Fluorine, recall, is the most electronegative element, so it will really never give up electrons, it will always accept them. So fluorine will have a -1 oxidation number. The other halogens are usually -1 when they're negative, but they can also have positive oxidation numbers, as you'll see in a minute, in these oxy-ions. So things like chlorate, for example, or perchlorate, and many from the P block. There's a lot of variation in the P block. So you'll see that chlorine can actually take up on many different oxidation numbers, depending on the compound in which it is found. The sum of the oxidation numbers in a neutral compound is always 0. So this means in water, the total of the two hydrogens and of the one oxygen equals 0. And so we can account for both the hydrogen and the oxygen from the sum. And then the sum of the oxidation numbers in a polyatomic ion is the charge on the ion. So for example, carbonate, both the carbon and 3 oxygens have a total sum of charge of -2. That's kind of the idea. Okay, why don't we apply this concept in a problem. And here it says, in the nickel-cadmium battery, it uses the following redox reaction to generate electricity, and they want us to identify the substance that's oxidized, the substance that's reduced, and then indicate the oxidizing agent and the reducing agent. In order for us to do this, let's go ahead and assign oxidation numbers. Now cadmium on the left side, since it is an elemental, will have an oxidation number of 0. Anything in its elemental state is 0. Next, let's take a look at nickel here. Now nickel is teamed up with two oxygens. Recall that we said each oxygen has a -2 charge. So you get two oxygens, each with a -2 charge. Nickel therefore must be, in order to balance them out, a +4. So nickel is +4 here. In the case of water, water is always -2 on the oxygen and +1 on the hydrogen. So hydrogen is +1. On the right side of the equation, if you take a look, the hydroxide, you can pull the hydroxide out. The whole hydroxide polyatomic has a -1 charge. Now, there are two of them. This makes cadmium be +2 because there are two hydroxides. But you can break apart even the hydroxide. If the hydroxide breaks into oxygen and a hydrogen, the oxygen is a -2, the hydrogen is a +1. That's how you get the total -1. But notice that oxygen and hydrogen here were all also +2 and -2, I'm sorry, and +1. So there's really no need to break apart the OH. We'll assume that hydrogen is +1, oxygen is -2. So cadmium is a +2 charge here. Nickel, if you take a similar accounting, we got two hydroxides. Nickel will also be +2. So what we see now is going from the left to the right side, cadmium went from 0 to a +2, and if you recall, that's called oxidation. Your oxidation is losing electrons, oil. So cadmium is oxidized. And then if you take a look at nickel, nickel went from +4 down to a +2. That's reduction. So nickel got reduced. Now, if you remember, we said the substance that gets reduced can also be called the oxidizing agent, because as nickel gets reduced, it pulls electrons away from the cadmium, oxidizing the cadmium. So this is also called the oxidizing agent. And by contrast, cadmium then is called the reducing agent. The agent that reduces the other. So this is how you analyze a redox reaction to find who's being oxidized, who's being reduced. So this concludes for us lesson 1 of chapter 20.